Hello wonderful person, this is Anton, and today we're going to be talking about cosmic strings. Well, actually no, we're talking about a study that suggests we may have discovered cosmic strings somewhere out there in the universe. But it's actually a lot more complicated than that, as usual, so we're going to dissect this into little pieces. First of all, cosmic strings. Not to be confused with the somewhat famous string theory. Nothing to do with string theory whatsoever, at least not to the extent where they depend on each other. Cosmic strings are physical objects. They're objects that are to some extent predicted by the Einstein's theories, and they're also objects that have absolutely no need for any kind of special physics or special anything. They could exist simply based on the physics we understand right now. And I think the best way to understand what cosmic strings are is to understand how they might have been formed in the beginning of the universe. According to a lot of modern theories, when the universe was just sort of created and a lot of early conditions started to change, for example, new forces started to appear, such as the strong, the weak, and the electromagnetic force, this early universe started to undergo a kind of a phase shift, essentially similar to how water turns into ice or how water can turn into gas. Things in the universe started to change as well, mostly because it was cooling down. And so because of this, different theories predict that there was most likely some sort of what's known as a topological defect, or basically a breaking of symmetry due to the sudden changes in conditions. Now, this might sound complicated, but it's really not. We've all seen this many times around us. Here's the most typical example, the ice cracks. Ice cracks happen when the phase shift occurs. They're also somewhat unpredictable, they look like long strings, and in some cases, they create a lot of unique geometric shapes. So this phase shift and the topological defects happen in various different conditions across the universe, and of course in various materials as well. In this case, this is from a paper about nanomaterials, so it even happens on extremely tiny scales. But what if we were to look at the universe as a whole? Can these cracks form in the universe itself as it sort of transitions from one phase to another? And this is exactly where the idea behind cosmic strings comes in. As the universe transitions from the early stage into the later stages, and as it starts evolving more and more, the phase shift in the universe could lead to the formation of these topological defects and create these very thin, almost one-dimensional strings, only a thickness of a typical proton, but lengths of anywhere from a few kilometers to possibly even a few light years. Strings that, just like every other string we know of, would vibrate and would also release energy through these vibrations. And even though these strings are believed to be extremely thin, they would still be super dense. They would be so dense, as a matter of fact, that they would actually produce gravitational effects visible from anywhere in the universe. In other words, there are ways for us to prove if these cosmic strings exist. And because of the high density here, a string that's only about a kilometer in length would be as massive as planet Earth. This of course means that even short strings would produce really large gravitational effects. And as the universe grew in size and as things sort of separated, these strings most likely grew in size as well. Although some of them might have started to kind of loop on one another, some of them might have even collided or combined with one another, and may have even created all sorts of loops, all sorts of unusual complex shapes, all of which would start releasing tremendous amounts of energy that could be detected from Earth. This type of energy, as you can imagine, would not be energy that we can see. This wouldn't be any kind of a solar radiation or any kind of radiation from a black hole. It would be, however, visible using gravitational wave detectors. In other words, it would be gravitational energy, very similar to the gravitational waves we've been detecting when two black holes or two neutron stars collide. And the theory suggests that even a single string would still be vibrating and producing these gravitational waves constantly, meaning that we should be able to see these coming from every single direction at all times. But since we've been detecting gravitational waves from collisions of black holes for several years now, and we've been really good at detecting at least one per week, how is it that we haven't seen any cosmic strings? Well, it really has to do with the frequency of detection. Black hole or neutron star collision produces a very fast in terms of frequency collision with the gravitational waves of high frequency that we can detect with the LIGO detector. But the gravitational waves produced by cosmic strings would be in much lower frequencies, somewhat similar to the gravitational waves we expect to detect from, for example, a supermassive black hole collision. This is currently beyond our abilities. For this, the LIGO detector would have to be thousands and possibly even millions of times bigger in size, so we can't really detect them using this technique. We can, however, detect them using a very different technique, using pulsars. And this is exactly what the recent study was able to do. So first of all, there is a very interesting observation going on, or I guess you can call it a survey, known as NanoGrav, North American Nanohertz Observatory for Gravitational Waves. It recently released approximately 12.5 years of observational data that allowed the scientists to see if any gravitational waves were detected by looking at various pulsars across the night skies. Now, pulsars, as you might know, are very unique objects. They're extremely predictable. So predictable, as a matter of fact, that every single pulsation is more accurate than the most accurate atomic clock on the planet. Although not for all of them, but for most of them. It's so accurate, as a matter of fact, that when the first pulsar was discovered back in 1967, the very predictable frequencies that Jocelyn Burnell was detecting by looking at something unusual in the night skies at first made her believe that it could have been even aliens. They even referred to this as LGM, Little Green Men. But with time, LGM became known as the first pulsar ever discovered. This was back in 1967, and we've discovered quite a lot of them since. And so if we were to look at all of the pulsars around us and to try to measure their pulsations extremely accurately, and then try to see if any deviations happen in those pulsations, we can actually start seeing different gravitational waves causing the changes in pulsations. Because naturally, if a gravitational wave passes in between the pulsar, or technically its beam, and Earth, we'll be able to see slight variations. And the recent release from NanoGrav seems to have identified unusual unexplained gravitational waves that have been affecting various pulsars in our galaxy. Now, there could be, of course, other explanations, such as maybe this is a collision between two supermassive black holes that have been sending all of these gravitational waves across our galaxy. But another more interesting and to some extent even more likely explanation, other than of course this being just data error or some mistake in the processing of the data, was identified in a paper you can find in the description below. They believe that this is the official detection of the cosmic strings. Essentially, what this suggests is that a cosmic string is probably sort of stretched across our galaxy and probably connected to some other cosmic strings, and as it vibrates and as it loses energy, it produces these gravitational waves we're observing. Now, obviously, it doesn't have to be just black holes and just cosmic strings. It could be some other unusual phenomenon, possibly some other unusual cosmic catastrophe that happened somewhere else in the universe. But as it stands right now, cosmic strings is one of the possible and very likely explanations. As a matter of fact, NanoGrav's main goal has been to try to discover both supermassive black hole collisions and cosmic strings. So in that sense, we might have just discovered exactly what we were looking for. But because this is science, we can't really rush into this saying that this is exactly what it is. There is a slight possibility that it could be a problem with the measurements here on Earth, so some of the observations have to be confirmed first, and at the same time, it could also be some unusual property that we previously did not know about coming from the pulsars themselves. Maybe they're actually causing this without us knowing about it. But naturally, this is the most exciting explanation. Cosmic strings, if discovered, would create a completely new area of study for astronomy and would allow us to try to discover if we can somehow use them here on Earth as well. Although, chances are, we're still way far away from any of this ever happening. But since these objects could technically be forming approximately 10% of the entire universe, it does mean that we should be able to detect them at some point, assuming of course they're real. Some scientists even propose that maybe cosmic strings are the reason why galaxies clump together to begin with. So it was sort of a combination between dark matter and cosmic strings acting together and forming these extremely beautiful galactic structures that we have everywhere in the universe. Although right now the only way we can prove or disprove this is by getting even more data from NanoGrav and possibly observing even more pulsars to see if they also exhibit similar effects. For now, we can't really say what we just saw. However, there was a previous detection or a possible detection of a cosmic string a few years ago. This was actually from a twin quasar or a twin very bright galaxy you see right here, known as Q0957. What's interesting about this object is that these are double quasars, but what's more unusual is that they're extremely similar to each other. They're twins, and this led to a belief that maybe these are actually the same object. It's an object that was reflected by something. In other words, this is a mirror image of a distant galaxy. But what created this mirror? Well, some scientists believe that maybe this was a cosmic string passing between Earth and a distant quasar that allowed it to reflect in such a way. And although this is a relatively old paper and there haven't really been a lot of follow-ups about this, we still don't really know what exactly happened here. Either way though, it's a really interesting discovery, but a more interesting discovery would be the cosmic string itself. So hopefully one day we'll be able to find out what exactly happened here, and if a cosmic string was indeed responsible for causing this unusual reflection. How many galaxies are there in total in the visible observable universe? And that's a question that's almost impossible to answer, at least at the moment. Because when you really think about it, it's actually very difficult to count the total number. As a matter of fact, if you were to start counting at least one galaxy per second right now, you might get to about 2 billion, maybe 3 billion galaxies by the time you reach the last days of your life. And that kind of gives you an idea that there are a lot of galaxies. And those 3 billion galaxies that you might be able to count to, that's just a tiny amount compared to what we believe is out there. Now, interestingly, when I was still at school, we were always told there are approximately 100 billion galaxies out there, at least in the visible universe that we can see, not the invisible, unobservable universe that's beyond our reach already. And this idea of observable universe is essentially because the universe is expanding and some of the edges of the visible universe are slowly disappearing from our view. Which of course means that there are still a lot more galaxies in the unobservable invisible universe, but by definition we'll never really be able to see it, and even more galaxies are going to become unobservable with time. But even in the visible universe, there are a lot of different types of galaxies, and even here, at least right now, it's almost impossible for us to truly know how many of them there are. We just know that there are a lot of them, and that they also come in different shapes and sizes. Some being more typical, similar to the one we live in, some being a little bit more unusual, and some being very different. As a matter of fact, in this particular galaxy, you can see that there's another smaller similar galaxy inside of it. Although in this case it's not really inside, it's much farther away, and it just so happens that they align together to create this view. But one of the first attempts to try to figure out how many galaxies there were was to essentially look at an extremely dark spot with the beautiful Hubble telescope, and then by trying to see how many galaxies we can see in this dark spot, the scientists tried to estimate the total number of all of the galaxies in the entire universe. And so using this image known as Hubble Ultra Deep Field, the scientists were able to estimate the number at around 100 billion to maybe 400 billion at the max. But that was years ago, and since then this value has slowly been going up. Specifically, only a few years ago, back in 2016, another interesting study used what's known as the galactic density to try to create a new estimate. And back then the scientists realized that we were off by at least a zero. In other words, there were possibly about 2 trillion galaxies, 10 times more than we initially anticipated. Just to give you perspective here, if once again you sat down and started counting one galaxy per second, and essentially just looking at each of these galaxies for 1 second, and you wanted to cover all of these 2 trillion galaxies, it would take you about 64,000 years. And yeah, nobody has time for that. So we have to figure out a much better way of doing this, and with time we started to get more and more techniques. And one interesting way we could actually try to estimate the total number of galaxies is by essentially trying to see how much total light we can get in a certain location in the darkness of space. In other words, let's just say we look at different spots and we try to calculate the total amount of luminosity received in a certain frequency. For example, in optical light that we can usually see. By then trying to estimate how much light we can get everywhere in the universe, we can kind of estimate how much gas and how much different types of stars should be emitting this type of light. And so in some sense it's sort of like looking at the cosmic microwave background and trying to get the microwave background of the universe, but instead of the microwaves, here we're using visible light. And normally the scientists refer to this as cosmic optical background. And this technique has been previously used many times, even by Hubble telescope, although unfortunately the problem with Hubble is that it's really good at looking at far away and very hard to see objects, but it's not so good at looking at nothing, at looking at complete emptiness and trying to see just light coming out of nowhere. But in the past, scientists still have tried this with Hubble telescope. They've also tried this with the Pioneer probes, with the Voyager probes, and even ground telescopes. But the problem is, if you were to measure this optical light close to planet Earth, you unfortunately start seeing a lot of light scattering from tiny particles, usually orbiting in the vicinity of the planet. So basically all kinds of different micrometeorites, all sorts of microscopic dust, and interplanetary material. So really it kind of helps to go really far away from the sun, and the farther the better. Because if you could reach a point in space where it's extremely dark and almost no particles are present, you can see the complete darkness of space, and thus calculate the total cosmic optical background, which would then naturally help you estimate the total number of galaxies out there. And it just so happens that we do have a probe that has an extremely good camera and is also really far away from planet Earth and from the Sun. As you can probably guess, the New Horizons probe. The probe that even at these distances have been actually conducting a lot of really good science and returning a lot of amazing data. One of the more important instruments on board the probe is what's known as the LORI, Long Range Reconnaissance Imager. It's what allowed us to take all of these incredible detailed pictures of Pluto, and is essentially the most complex camera currently so far away from the Sun. It also happens to be in an extremely dark environment, really far away from anything bright, which of course presents this as an opportunity to once again try to study this so-called cosmic optical background and try to find out how dark, or in some sense how bright, the darkness of the universe actually is. In other words, an attempt to find out how many galaxies are out there. And it looks like now we have an answer from the paper you can find in the description below. By doing this several times and looking at these 7 specific locations around the galaxy, and by essentially looking at complete darkness and then studying the average light in this darkness, in the location that seems to be approximately 10 times darker on average than the location where Hubble was able to do it, the scientists in this paper were able to see that there is a lot of unusual diffuse light that wasn't actually visible before. In other words, there was more light coming from these dark spots than the scientists originally anticipated, approximately double the amount. And what this implied is that there seem to be a lot more undiscovered galaxies than even the 2016 paper predicted, suggesting that the overall limit of total galaxies is maybe closer to about 4 trillion, or possibly even more. Once again, if you were to count them one by one every second, it would take you about 130,000 years. However, here we have to be careful, because this diffuse light could have come from some completely different phenomenon. For all we know, maybe this brightness is actually caused by some other mysterious phenomenon, like maybe dark matter. Maybe this is what dark matter is producing at these far away distances, and it's not so dark after all. On the other hand, it can also be related to just the gas itself, located in various intergalactic spaces. In other words, there is a chance that maybe what we're looking at is the light produced by intergalactic cosmic web. At the moment, there's really no way to find out what exactly is causing all of this. It seems to be really there, and the galaxy has twice whatever it is that we thought was there. And remember, here we're only talking about the observable universe. Still, so much more is invisible to us, and we'll never be able to see anything beyond this observable universe. So the total true number of galaxies out there in the entire universe that's beyond our observable limits is completely mind-blowing. As a matter of fact, it could even be maybe infinite, if that's a thing. But that's not something we're going to speculate about, because we really have no means of knowing this. We can, however, try to calculate the limit of observable universe, and here, at the moment, the number stands at maybe 4 trillion. At least for now, as of 2020. I'm sure in about 4 years, even better calculations, even better discoveries, and better cameras will produce even more accurate results. And for all we know, maybe another 0 will have to be added to this number. Either way, it's pretty incredible how far we've come in our ability to try to estimate the amount of stuff out there in the universe. I mean, I guess you'd think that it's easy to calculate the galaxies, at least because they're pretty easily visible. But remember, because of the sheer number of them, and also because a lot of them become pretty much invisible at faraway distances, it really becomes kind of difficult to estimate these unusual numbers and unusual properties. And so trying to get the estimate just using the total brightness of a dark region is, at the moment, the best technique that we have. And it looks like the number for this is once again about 4 trillion. And think of something extremely big. What is the largest thing you can think of? How about the largest thing in the world? Alright? What about the biggest planet? What about the biggest star? Biggest galaxy? Well, all of those we've actually covered on the channel before, with the last one being the famous IC1101. The galaxy is so ridiculously large that our own Milky Way would only appear as a tiny star-like object you see right there next to it. So these objects are obviously quite large, but they're not even close to being some of the largest objects we've discovered so far. And this is actually the realm of the science known as cosmography. And today I wanted to talk about the recent discovery of what seems to be one of the largest objects ever discovered, possibly 5th largest ever, and this is known as the South Pole Wall. This is an object that's so much larger than anything we can even think of that it is literally going to blow your mind. So let's talk about this and welcome to What the Math. Now the team behind the study actually has a really interesting video you can check out in the description below as well. And this is a video that shows you how they essentially process the information from around us, from the night skies, and then change it into the three-dimensional maps that allow us to see these structures in detail. But just showing you one picture of the size of this object is unfortunately not going to give you a perspective of how big this thing is. So let's try this step by step. Let's start right here with obviously something a little bit more familiar, planet Earth and the Moon. Zoom out far enough and Earth is now just a tiny pixel and you get to see the inner solar system. Zoom out just as much and you now get to see the outer solar system. So this kind of gives you an idea that solar system is already pretty big. Now we need to really start zooming out even more until we start seeing the nearby neighboring stars. The distances here are now in light years. So for example, this right here is about 12.5 light years away from us. And these are already the distances we're currently unable to reach because of the technology limitations. Now if you were to zoom out over 1,000 times more, you would finally start seeing the entire Milky Way in all of its glory. This is essentially the galactic size, but we're not even close to being there yet. We're going to zoom out even more to now start seeing the so-called local group of galaxies. This is our neighbors, this is the galaxies connected to us, and this includes the famous Andromeda galaxy, which is right here, and the slightly less famous Triangulum galaxy that's also right here. Both of these will be colliding with us in the next few billion years. And now we have to start zooming out even more once again, in order for us to reach the so-called cluster or supercluster group. This is essentially thousands and thousands of galaxies all together connected to one another, and the team behind this new discovery a few years ago also announced that all of our galaxies are actually connected together as a supercluster they named Laniakea. The Milky Way galaxy is somewhere right here on the corner, and essentially all of these galaxies are all moving together into the same direction and are also all gravitationally connected to one another, so technically it's a single object because they do have a very specific gravitational interaction with one another. But obviously these are not molecular objects, these are not objects that are connected to each other through molecular forces. These are objects that are connected gravitationally, and they maintain their shape and of course their motion through various gravitational and possibly even electromagnetic interactions. The size of this object is about 500 million light years, or roughly around 520 million light years in width. It contains a mass of about 100 million billion suns and, well, it's already a really large object, but we're not there yet. We have to zoom out a little bit more to start seeing other superclusters and other really large objects. And so this is the scale where we've discovered a new object. And this one is about 3 times bigger than Laniakea that I just showed you. This so-called South Pole Wall was originally thought to be much smaller, but we've recently discovered that it's a lot bigger than scientists believed. It's about 1.4 billion light years in length, making this one of the biggest objects we've ever found. And in case you were curious, the biggest object is roughly around 5 times bigger than South Pole Wall and is known as the Hercules Corona Borealis Great Wall. So it's a very similar type of a concept. It's essentially a connection of galaxies and superclusters forming this very, very large structure. And it's also about 20 times bigger than Laniakea right here. But nevertheless, it is something that's extremely difficult for human mind to imagine. It's something that's so extremely large and so difficult to even simulate that currently our brains are not really able to understand it very well. But in most cases, we usually define these objects by their gravitational connection and also by their overall motion. And so in most cases, all of these objects are basically kind of all sticking together and they're all moving towards something unknown somewhere in the universe. For example, for Laniakea, as you can see right here, it's all moving toward the so-called Great Attractor. We don't really know what it is, but it's something that's attracting all of the galaxies nearby. But let's just say you wanted to try to imagine it by looking into the night skies and by really trying to see how big this South Pole wall was. Let me help you by looking at various constellations. Here we only need to find two constellations, Apus and Lepus. And right between them is this imaginary South Pole wall that's really far away, billions of light years away from us. So here, if we look at constellation Lepus, which is right here, and then try to trace all of this way until we discover Apus, which is, I believe, somewhere right, maybe somewhere here. Here it comes. Here's Apus. That is the distance where this wall is located. That is a really large part of the night skies. And so from here all the way to back here, that's essentially the size of this Great Wall. And one of the reasons we've only discovered its true size today, and we didn't really know about its true size before, is because a large part of it was actually hiding behind the somewhat difficult to see region of space right here where the Milky Way itself is. And this is the center of our galaxy that has a lot of different gas that's actually hiding a huge part of the universe for us to investigate. And some of the recent studies were able to see through this gas and were able to see very distant galaxies hiding there, allowing the cosmographers to establish the connection between them and thus realize how extremely large this shape was and how a lot of it was actually just hidden from us. And although not the largest structure ever discovered, it's still quite there. It's one of the biggest structures in the universe and is at least 3 times bigger than the supercluster where we are located, which is honestly a pretty big discovery for cosmography and for our understanding of the shape of the universe itself. But the thing is, as we learn more about the universe around us and as we start understanding the various directions and motion and a lot of interaction between various parts of the universe, we'll finally possibly be able to answer some of the other questions that we haven't really been able to answer. In the past 2 years, a lot of new observations suggested that the universe itself might not even be uniform, so understanding this motion is really important for us to establish what's going on in the universe and where is it expanding, how is it moving, and most importantly, if the physics we know here on Earth apply to the rest of the universe as well. Which is actually something that was questioned in one of the previous studies in the video you can check out on the channel about the so-called fine structure constant. So hopefully with time we'll be able to map the entire universe even better and we'll be able to understand what is actually happening and also historically answer the questions of what happened in a universe and most importantly, what will happen in the future. And today we're going to be talking about the structure of the universe. But actually, we're going to compare the structure of the universe to the structure of something we all have. A brain. Although I'm sure someone in the comments is going to make a joke about this. But anyway, it's actually based on this picture that was trending on Facebook and other social media a few years ago, essentially comparing the structure of our own brain to the structure of the universe. With the picture on the right originally being created by this Virgo consortium that usually produces a lot of supercomputer simulations, with the website that for some reason also does this. I could not figure out why it does that though. And the picture on the left, the cross-section of our brain, is something that this wonderful person Mark Miller created a long time ago for his PhD thesis, and he actually has quite a lot of these pictures, more of which you can discover on his account in the description below. And the thing is, back in the days, I think when most of us saw this, a lot of us probably went, wow, that's cool, But how true is this, and also what does this all mean? Well, first of all, a really quick clarification. This really has nothing to do with consciousness, this has nothing to do with intelligence, and we're not really going to be talking about the idea of intelligent universe or some sort of a higher being somewhere out there. There's absolutely no way for us to prove any of this, and we actually have no idea how even our own consciousness is created. So this is sort of beyond the scope of the video. But what we are going to be talking about is the structure. The complexity of different networks, the complexity of structures as they arise from pretty much nothing, and how these structures seem to actually resemble one another even though the size itself is very different. Which is essentially what the scientists who created these images wanted to actually underline as well, and most importantly, someone finally did the science behind all of this and identified several major similarities and also obviously some differences as well between what seems to be the structure in our brain and the structure of the universe. And that's of course the paper you can find in the description as well. And what makes the study particularly interesting is that it was actually an astrophysicist and a neurosurgeon combining their knowledge and combining their expertise to try to create the similarities between the brain and the universe. So it's not just a picture on Facebook, this is actually true science. And all of this of course connects to the idea that there are just a lot of different patterns and a lot of different networks everywhere around us, and many of these networks seem to follow a very similar principle, usually mathematical principle, creating very beautiful but also very repetitive patterns that can then be discovered in different domains around us. And by the way, a lot of the imagery I'm using here and also a lot of the simulations is from the amazing Illustris project that's really good at creating these patterns, recreating our own universe. But once again, let me highlight this again. The morphology or the shape of things does not imply that the function is the same. In other words, just because two things resemble each other, it does not mean that they're going to have the same function. But anyway, let's move on with the similarities. And so interestingly here, we actually know a lot more about the universe than we technically know about the structure and the formation of the structure in the brain. And so in some sense, by studying how all of this is done in the universe, it actually does help us realize how everything forms inside of our brain as well. For example, like you see in this image from Hubble telescope, galaxies tend to actually bunch together into clusters and superclusters. And these clusters usually also have connections between one another, which we normally call cosmic webs. None of this is easily visible, but we know it's there because it's been discovered and rediscovered by many different studies. But we also know that between these clusters, there's usually a lot of empty space. So for example, right here, or pretty much everywhere where you don't see anything, which is slightly easier to see in this simulation that shows you the connections and the galaxies, and also the voids in between them. And right between the voids and the galaxies, there's actually quite a lot of complexity and a lot of really fast moving particles, a lot of really complex matter interaction, and a lot of complex turbulence usually caused by the gravity itself. But all of this complexity is also to some extent reflected by what we can find inside the brain as well. And even though pictures taken by Mark Miller represent something that's approximately 1 followed by 27 zeros smaller than what you see right here created by the Illustris project, there are very specific similarities that go beyond just the look itself. Now, first of all, today we know that even though there are a lot of different types of matter in the universe, there are even things like dark matter, for the most part, the majority of the universe is made up of what's known as dark energy. At least that's what we believe today based on all of the observations and all of the analysis. We don't really know what it is, but it seems to represent at least 68 or possibly even up to 72% of everything in the universe. Okay, well that's interesting, because at the same time, if you were to look inside the brain, as you can see inside this MRI video from Navid Tillman, about 77% of our brain is essentially water, although in this case what you're looking at is the so-called cerebrospinal fluid, which also moderates a lot of activity in the brain and is responsible for essentially maintaining a lot of the brain's functionality. And at the same time, another really interesting similarity here is in regards to the flow of information and energy in both systems. So in the brain and in the universe, the flow of energy and the flow of various types of information in both neurons and the universe represents roughly around 25% of the entire mass and energy content of the object. At the same time, when we compare a size of a typical galaxy with the size of the actual galactic filament, or the so-called cosmic web. And then if we also compare the actual size of neurons and neuronal axons, which are these long projections you see, the length proportion seems to be almost identical. In other words, by making the brain about the same size as the universe, a typical neuron would represent a galaxy, and neuronal axon would be long enough to represent the cosmic web. Also, not surprisingly, both the brain and the universe are inside specifically defined networks, which also resemble one another quite a lot, with each of the neurons and each of the galaxies possessing a relatively similar number of connections, surprisingly. So for example, inside the brain, when looking at approximately 2000 different nodes, the scientists discovered that each of those nodes was making anywhere between 4.6 and 5.4, or basically average of about 5 different connections. So every neuron was connected to roughly around 5 other neurons. And then, when looking at the structure of the universe, a very similar pattern emerged. By looking at around 4,000 different nodes, they discovered an average of about 4 connections, so maybe a little bit less than the brain, but very similar, 4 versus 5. And what's more is that both structures have a preference for clustering a lot of things around some sort of a central node. So basically what we would call a cluster of galaxies seems to also exist in the brain, although unfortunately it's very difficult to find good pictures of this. Once again, if you would like to see more, check out Mark Miller's Flickr page because it does have some of the best imagery I've found so far. And then we come to the question of numbers. So the estimates right now suggest that there are approximately 70 billion different neurons in our brain. And the previous numbers for the number of galaxies in the observable universe was anywhere from 100 to 400 billion, although today we think it's much higher, possibly even 4 trillion. So in that sense, the numbers for galaxies, at least in the observable universe, seems to be higher. But at the same time, we're just talking about the observable universe and we don't really know the true numbers in the entire universe. As a matter of fact, we probably never will. And so in that sense, knowing that the number of neurons is not so far off from the number of galaxies in the observable universe is also extremely unusual. Although unusual is maybe not the right word. Mind-blowing is a much better word. Also, interestingly, about 75% of everything in the brain and in the universe is made out of passive materials that don't seem to influence things as much. They do have certain fluctuations that influence the bigger scale of things, but both structures seem to possess something. Either different types of gas motion, for example, in the universe, or different types of neuronal signals in the brain. And in this case, when scientists looked at approximately 1 micrometer of neuronal tissue and compared it to about 5 million light years of galaxies, the actual fluctuations and activity was extremely similar in morphology. In other words, even the passive activity and a lot of different motion was somewhat similar to one another. And then there's also the question of information. For example, we know today that our brain can, hypothetically at least, store about 2.5 petabytes of information, which is about 2,500 terabytes. And when it comes to the complexity of connections inside the universe, if we were to apply a similar principle here, the total information in the visible universe would be about 4.5 petabytes. So just a little bit more, but not a lot more. Although here we're just talking about the possible connections between things and not the true formation of memory, for example, not the true formation of information. Here we're just talking about links between different nodes. But just like I mentioned before, it's still very easy to make a wrong conclusion here. The brain structure does not mean that the universe is also aware or that the universe has consciousness. This study only explains one thing. It seems that structures, especially very large structures, follow exactly the same rules when it comes to formation and networking. The complexity and the self-organization inside of these structures create pretty much similar ideas and similar results. Which of course doesn't really help us answer the question of consciousness at all. It just helps us, well, not really much as a matter of fact. It does help us understand how maybe complex AI networks could form and how we could maybe create some sort of a really complex computer simulation, but in this case it does not help us in any other way other than just seeing something similar in terms of morphology or how things look. Nevertheless, I personally found it to be a pretty cool analysis, and the paper and all of the relevant links are, as always, in the description below. But on that note, that's kind of all I wanted to mention. It's pretty awesome that we're finding these links and networks and all of these different connections pretty much everywhere around us, but it's also not surprising because these mathematical patterns do repeat themselves even if you look at something really microscopic or if you look at something really huge. That in essence is the math at work. Check out all of the papers and all of the links in the description below, and also check out the work by Mark Miller or by any of the other scientists I mentioned in this video. So there does seem to be something unusual going on with the structure of the universe, something the scientists currently can't explain. It actually all kind of started back in 2005-2006 when the scientists reported that there was a very unusual observation coming from the so-called cosmic microwave background, the most ancient light in the universe, that seemed to suggest that the universe had directions and also seemed to even have poles, kinda like, in a sense, axes of rotation or some sort of axis around which things were spinning. And this by itself led to quite a lot of different counter-studies and different discussions that haven't really resulted in anything since. This is still sort of unexplained. At the same time, several other studies even discovered a lot of other unusual patterns, like for example changes in various constants, such as the cosmological constant, across the universe. In other words, things in the universe don't seem to act, or they don't seem to be, in the way we always believed them to be. Even though we always assumed the universe itself was sort of isotropic, it's more or less equal everywhere, it's sort of chaotic and unpredictable and doesn't really have any structure, a lot of various observations from the past few years suggest otherwise. Some of the scientists even coined this unusual and somewhat inappropriate term axis of evil to explain the unusual observations of what seem to be poles, or basically the axis of rotation, but not for a galaxy, not for a star system, for the entire universe. Now, just to add to all of this, the recent discovery coming from the Kansas State University discovered something else unusual that is going to be really difficult to disprove. Mostly because it's really easy to observe using any telescope. Essentially, this time the scientists behind this paper looked at the spin of different galaxies. And just to explain this to you really easily, so, okay, if you were to look at any galaxy out there in the universe from our perspective here on Earth, you would see it spinning either this way, which is counterclockwise, or you would see it spinning this way, which would be clockwise. Now, if the universe is basically same everywhere, it's isotropic, it's sort of equal and chaotic and unpredictable, you would statistically find both clockwise and counterclockwise galaxies in pretty much equal amounts across the entire universe. So no matter where you look in every direction, you should be able to see the equal amount of counterclockwise and clockwise galaxies, or spinning galaxies that is. But if you were to try to count all of this by hand, it would basically take you your whole life and even longer. So this is why the scientists behind this particular paper used the automated search system, specifically the two telescopes known as PanSTARRS, or Panoramic Survey Telescope and Rapid Response System, and SDSS, or Sloan Digital Sky Survey. Both of these systems are set up to search for various features automatically and can basically search through millions and millions of galaxies, or really any other objects, within only a few minutes or possibly hours. And this is something that scientists have used many times in the past as well. And so by using these two telescopes, the researcher behind this paper decided to take a look at really just one feature. He wanted to investigate the spins of galaxies in terms of direction. And to his surprise, he discovered there was a pattern, specifically several different patterns. And if you were to summarize his discoveries in one picture, it would look something like this. Here, this shows you the entire night skies, and every single color denotes the chance for a certain spin to be either more clockwise or more counterclockwise. And it seems that there are certain directions in the night skies where there is a prevalence for example, clockwise or counterclockwise galaxies. And in this case, it's not just two axes either, it seems to be a multiple direction. In other words, if you were to look in a certain direction in the universe, you would discover that galaxies in this particular part would spin more clockwise. Whereas if you were to look in the exactly opposite direction, you would find them to spin counterclockwise. And there's at least one more direction that seems to have a very similar pattern. Now this currently has no explanation, but there's one little thing I need to kind of add to all of this. the actual differences are not really super dramatic. We're not talking about like all of the galaxies here spin clockwise and all of the galaxies in the opposite direction spin counterclockwise. The actual difference is only about 1% or so. So if statistically we kind of imagine the galaxies in this direction to spin 50% clockwise and counterclockwise, in his study he discovers that about 51% of galaxies spin clockwise, whereas 49% spin counterclockwise. So it's really only a 1% difference, but by chance, it's almost impossible for this to happen. The chance is only like 1 in 1 billion. So as it stands right now, it's pretty much almost completely impossible for this to be a chance. It's very likely that something is going on here, especially because when looking at various galaxies, he discovered that nearby galaxies, the galaxies relatively close to us, were more or less equally distributed. The basically isotropy of the nearby universe was pretty high. Whereas once you move further and further back in time to the earlier universe, the chance for this clockwise/counterclockwise positioning increases quite dramatically. And this does have a really important implication. All of this basically suggests that back when the universe was still younger, something was governing its, in a sense, spin. Something was changing its direction, and it may have even been spinning altogether. Or the early universe was a lot more orderly and a lot more structured than the current universe. And this is, of course, something we currently cannot explain. And this is something we've been discovering more and more in the last few years. It has no explanation, we don't really know what's happening, but it does seem to suggest that there is a bit more order to the universe than we originally assumed. So when the universe was just created right after the Big Bang, the actual structure was much more orderly and may have even been spinning. Now, there are possibly other explanations to what exactly is causing these unusual observations and these patterns, and more specifically what's causing these galaxies to spin in one direction or the other. And one potential explanation here that doesn't involve basically unexplained phenomena is essentially the so-called cosmic web, also known as the cosmic filament. The cosmic web sort of forms a really specific structure across the universe, and we do believe that it does have some kind of a pattern going on, we just don't really know what it is yet. This particular cosmic web is responsible for, well, actually governing how galaxies behave, how they spin, and more specifically, in the last few years we've discovered that the cosmic web is responsible for causing distant galaxies, quasars as they're known, to assume a certain rotation and a certain position across the cosmic web, and it even causes them to spin in a very specific direction. This is something we've observed several times now, so we know that something is definitely going on there. So there is a slight chance that maybe we're just aligned with the cosmic web in such a way that in one direction galaxies are spinning more clockwise, in the other one they spin more counterclockwise. So it could be just the actual axis of the cosmic web itself, not really some kind of unexplained rotation of the universe. However, it's still too early to tell, and we definitely need a lot more follow-up studies on this particular observation, which really shouldn't really be that hard because observing these spins of galaxies is pretty easy, to try to determine what's happening here and what exactly did the scientists here discover. But as of right now, it's yet another mystery of the universe. More specifically, the mystery of the order of the early universe. Something we didn't really know or think existed. And if this study actually did find something and the early universe was more orderly and was even spinning, there's going to be a lot more investigation we're going to need to do to try to discover why it was spinning, what exactly caused it to stop spinning, and more importantly, did this actually produce all of the other unusual anomalies we're observing or have observed in the past, and can we basically explain all of this, including the changes in constants, for example, as these unusual poles and these unusual axes of rotation of the entire universe. And of course, if this is all correct, then it would also suggest that our current understanding of the universe is a little bit too primitive. We assume that it was isotropic, it was same everywhere, but it seems to be a little bit different. Actually, a lot different. So first of all, when it comes to the universe, we've always kind of made an assumption that, for the most part, it seems to be kind of the same everywhere. More specifically, it seems to expand in every direction at relatively similar speed, or actually at the same speed. This is what a lot of modern physics is based on. But most importantly, it has actually been thoroughly proven many times, especially by looking at very distant objects, and more specifically by looking at the so-called cosmic microwave background, which does seem to indicate that the universe, for the most part, seems to be relatively similar all around us. But there is a problem with looking at these distant objects. Specifically, there is a problem with the CMB. It is really old. When this started to appear in the universe was only about 380,000 years old. So back then, maybe the universe was actually the same everywhere. But does that mean that the universe is still the same everywhere? Well, according to some of the recent studies, and more specifically this study right here that very recently came out, it doesn't seem to be the case, and this kind of challenges a lot of facts that we've always taken for granted. And specifically, one thing that this study challenges is the idea that the universe is expanding in every direction at the same speed. The study in this case shows that the difference in the speed of expansion seems to be up to about 30% different, suggesting that if we were to look at different directions in the universe, we would actually see expansion happening at different speeds. And that is a bit of a problem because up to now, we've always made all of our calculations based on the assumption that everything around us is the same. So for example, if we were to look at a really distant galaxy, which we can do right now by jumping to a random galaxy really far away from us, here we've always made the mass calculations and the distance calculations based on the same principle that everything is expanding everywhere at the same rate. But if it doesn't, it actually challenges a lot of these calculations and puts them in a bit of a pickle, I guess. But let's briefly also talk about how exactly the scientists determined all of this. For this particular study, what the scientists behind this paper did was use a very well-known in astrophysics relationship between the amount of gas somewhere and the amount of X-ray radiation being released. This relationship has been confirmed in many different studies, but essentially here, the more gas we find somewhere in the universe, the more X-rays we'll discover. And this relationship is actually quite linear. So for example, if we were to look at these 4 galactic clusters you see right here, there is a direct relationship between the amount of gas present and the amount of X-rays each of them releases. And this relationship can obviously be quantified, and we can definitely create all kinds of graphs trying to establish how much gas versus how much X-rays there are. And so for this particular study, the scientists behind this paper chose 313 different galactic clusters, pretty much all across the night skies except for certain locations in the polar regions where they couldn't really have enough data. And they tried to analyze 2 types of relationships. First of all, they've established the relationship between the amount of gas and the X-ray brightness. So basically, here for example, let's just say we go to this galactic cluster and we measure the entire amount of X-ray radiation that's produced here. In this case, we can't really see it because this is just visual light, but they were able to use a lot of different data from different telescopes, including the so-called XMM Newton and the Chandra telescope. Oh, and also another German telescope known as Rosat. So by looking through all of this data and also combining all of this data into a really large table that you can actually find in their paper, they were able to create a relatively accurate representation of every single galactic cluster and every single measurement for the amount of X-ray luminosity that was produced by every one of these clusters. And well, to their surprise, what they discovered was that there was actually a very unusual discrepancy. In certain areas, certain luminosities were either brighter or dimmer than they should have been, as if these large regions of space were either moving away from us or moving toward us at certain velocities. In other words, they were able to create this relatively accurate map of the discrepancy across the entire map of the universe, which actually showed us, or showed them that is, that the expansion shape of the universe is not uniform. It seems to be expanding faster in certain locations and slower in other locations. And that is somewhat hard to explain and actually currently creates a lot of problems for us, because this means that in those particular locations we may have underestimated or overestimated certain galactic properties. But does this actually contradict the previous studies related to the CMB? Well, not really, because what this is showing us is that even though the universe used to expand pretty much equally in all directions, it has changed over time and now seems to expand differently in different locations, and that is something we currently can't explain. Now, one really important side note here, remember, this is only the first such study, so a lot of confirmation and possibly explanation is still needed to really determine what's happening here. The scientists themselves actually do mention this in the paper, and they do provide at least one opportunity for possibly having a mistake in the study. So there could have been some sort of a mistake somewhere. But it's still a really major discovery, and a lot of scientists will probably be focusing on this right now, because it does present us with a kind of a serious problem in terms of mass and distance and of course size calculations we've been making about other galaxies in the universe. And if for some unknown reason the universe is not the same in every direction, we still need to find a way to try to explain all of this as well. One of the potential explanations is that when the so-called dark energy was created, about which we unfortunately know very little, maybe it was created in different amounts across the universe. Now, because we don't know what dark energy is, what it could possibly be made out of, or if it even exists, this obviously creates a lot more problems as well. So right now we kind of don't really know what's happening here, but one first thing we need to do is confirm this study and find out if what they're seeing is actually accurate. Because if these unusual patterns are actually correct, and for example, in one direction we're seeing 30% less motion than in the other direction, so in other words, the universe is not expanding at the same speed at all, yet it was actually expanding at the same speed when the CMB was created, this, of course, needs to have some sort of a natural explanation, or at least some sort of a theory that can explain why the universe was created so unequally. But apart from dark energy distribution and possible mistakes in the study, another explanation here is the so-called dark flow. Now, I briefly talked about this in one of the previous videos, but essentially dark flow refers to this unusual gravitational attractor that's actually beyond the visible universe. In other words, it's sort of past the actual sphere of the entire universe that we can see. And this whatever gravitational attractor thing seems to be actually attracting a lot of galactic clusters toward it, reshaping how the universe behaves in that particular area. So it's quite possible that what we're observing here are actually the effects of various dark flows across the universe that seem to reshape how galactic clusters are moving and are thus creating all sorts of possible problems for our calculations later on. Now we have a similar, I guess you can call it phenomenon here in our own galactic neighborhood, and it's actually called the Great Attractor. You can kind of see it right here, and there's even a bigger one known as Shapeless Attractor. Both of these are these extremely large gravitational phenomena or anomalies. We have no better word for it really, we don't really know what they are. They could be a collection of dark matter, they could be extremely massive black holes, but the only thing that seems to unify them is the idea of attracting a lot of matter toward them. And they do create these unusual flows across the universe, at least in the local neighborhood. So basically they're attracting like thousands and possibly even millions of various galaxies in this particular area. So it's actually quite possible that this is exactly what's happening here as well, but right now we actually really just don't know. We know that something's happening here, we have no idea how to explain it. And honestly, I think a lot of scientists are really hoping that this is just an error or a mistake, because otherwise it's going to create even more problems for cosmology that we currently can't really explain. But nevertheless, it is a great discovery and definitely something that a lot of scientists will be trying to investigate in the next few years. Long time ago, in a galaxy far away, something resulted in an extremely bright flash that we observed relatively recently. Something that the scientists now believe was a collision between two different black holes. Today we're going to be talking about one of the most unusual, the most unusual black hole collision we've ever detected, that not only involved two black holes we didn't think could possibly exist, but also resulted in some strange unusual effects we have never observed before. At the same time, the product of this collision was the first ever confirmed and detected intermediate mass black hole. And now that we know these giants exist, we can actually start hypothesizing about a lot of other black holes out there. But let's talk a little bit more about this, and welcome to the Math. Back in May of 2019, the detection of unusual gravitational waves by LIGO detector suggested that something massive once again collided with something else. but then another detector known as ZTF or Zwicky Transient Facility was able to see unusual light coming from this direction as well. At first it didn't really make sense, but the scientists detecting this started to hypothesize that maybe what we were observing was basically a collision of two black holes orbiting around another supermassive black hole, and the actual flash came from the disruption of the black hole as it moved through the accretion disk of the larger supermassive black hole. In other words, the scientists started to think that maybe we just observed the tremendously powerful explosion as a slightly less massive black hole passed through the accretion disk. And if so, the scientists also hypothesized we should be able to see it again in December of 2020 as it passes through the accretion disk again. But now the scientists recently were also able to analyze the masses of these two black holes and discovered that, well, they don't really make sense. The mass of these two black holes is, as you can see, 85 and 66 masses of the Sun, resulting in the total mass of 142 masses of the Sun. This of course means that first of all it created the mysterious and never before seen intermediate mass black hole that we only suspected existed based on some other observations, and at the same time we now know that these so-called impossible mass black holes can exist as well. And the reason they're called impossible mass black holes is for a relatively simple reason. There's a limit to a star mass before it starts experiencing very unusual effects and is no longer capable of producing black holes. You can find more about this in another video that I made previously that should be popping up somewhere above my head, but in a nutshell, the star of a mass of about 130 masses of the Sun up to about 250 masses of the Sun goes through something we refer to as pair instability supernova, which actually leaves absolutely nothing behind. So there's actually a gap to how massive certain black holes can get. We always believed that there shouldn't really be any black holes, smaller black holes out there over a mass of about 65 masses of the Sun. But now you can kind of see that 66 and even 85 seems to be possible. And if a star produced these two black holes, it would be falling into that pair instability mass and should really not be producing black holes. So that's sort of the paradox right now. Now, if a star is even more massive than 250 masses of the Sun, like for example the famous R136A1 located in the nearby Large Magellanic Cloud, the supernova from this star would also most likely produce a really massive black hole. But at this point, it would sort of be an intermediate mass black hole. At least that's the theory behind this. We don't entirely know what happens to these larger stars, but we think that they do produce black holes too. But that's not really the point right now. The point is that this single event produced three very unusual observations. We were able to detect black holes we never thought existed, we were able to detect the first ever confirmed intermediate mass black hole, and we even saw some kind of a strange flash coming from the vicinity of this region as well. All of this right now doesn't make sense, but I'm sure we'll be able to explain this in the next few months or so. And just to give you a little bit more reference, here's what some of the other detections look like so far, and you can see that we've detected quite a lot of different neutron stars, which usually have a mass between 1 and 2 masses of the Sun. We've also seen quite a lot of smaller black holes, and here was the limit of some of the larger ones we've seen. But now we've seen this really massive one, which is really the most exciting and the most unusual of them all. Now, if it actually did happen very close to the supermassive black hole, where we believe a lot of these black hole collisions happen to begin with, one possible explanation to how these black holes gain their mass that's not technically possible is because they collided with something else previously. Assuming that this is in the supermassive black hole region, and assuming that there are a lot of black holes orbiting around the supermassive black hole, they should have been colliding with one another for many billions of years. That's not something we think is unusual. However, it's not certain. And the other explanation here that actually relates to another video I made previously is in regards to the exotic geode objects, and I'm sure that the study about this is going to come out in the next few months. If you haven't seen this video, it's a video in regards to these exotic objects we refer to as geodes, the objects that are also responsible for the accelerated expansion of the universe. the objects that could also have been the culprits of this collision, because a collision between two geodes would be more or less unusual in terms of mass. It would actually be very close to what we've detected. At the same time, it could possibly produce a flash of energy, and most importantly, the unusual mass observation can easily be explained by the fact that this is a very distant explosion around 17 billion light years away from us, when the universe was about 5 billion years younger. During that period, a typical geode would actually acquire mass, making it around 60 to 80 masses of the Sun. Now, that's not something I'm going to be covering more in this video because this is sort of still theoretical and quite hypothetical, and we have no proof that geodes exist either. But in some of the future videos, we might explore this a little bit more. So let's get back into the facts. There is actually another unusual thing about this particular detection, and that's the actual sort of pitch that it created. Normally, if you've seen some of the other black hole collisions, you may know that black hole collisions seem to produce the so-called black hole chirp. It sort of looks and sounds like this. Now, these chirps are pretty common with all of the black hole collisions, but that's not what was produced here at all. As a matter of fact, when the scientists behind the study recreated the same type of a sound when these two black holes collided, which only lasted for like 1/10 of a second, the resulting sound was described as a thud, almost as if something really heavy just fell onto the floor. Now that's what makes this very unusual. It's sort of not what we expected at all, and it also sort of currently is difficult to explain. Which means that you can definitely expect a lot of follow-ups to this particular detection in some of the future videos. But the last unusual and somewhat mind-blowing discovery about this particular collision is the amount of energy that was released as the gravitational waves when these two black holes collided. Okay, let me try to help you imagine all of this. When a supernova occurs, when a very large and very massive star goes supernova, most of its mass normally ends up being completely redistributed across the galaxy. Only a very small fraction of the star releases the energy itself. The amount of energy released here is normally equivalent to the total energy our Sun is going to produce through its lifetime. So it's a lot, but it's not even close to how much energy is produced when these black holes collide. So when these two black holes collided, they released a total of about 8 to possibly even 9 masses of the Sun in energy. In terms of pure energy release, that's about 10 to maybe even 100,000 times higher than a typical supernova. But obviously this energy is not visible. This is gravitational energy, which is something that is difficult for us to imagine because we're not really able to think that way. Nevertheless, because we were also able to observe visual effects, maybe this also creates some other unusual effects we never thought of before. But all of this will be most likely discussed further in the future, most likely after December of 2020, when the scientists are able to prove or disprove if this particular flash was created when the black holes passed through the accretion disk. And so for now, we're left with a lot of questions, only some answers. It's a great observation, it's definitely something that the scientists were hoping to find. It's an incredible new observation, and it's surprisingly something the scientists thought they're not going to be able to see for decades. But we just did, only after about 5 or so years of operation of the LIGO detector. Which of course also means that we're going to be able to see a lot more unusual and strange unpredictable things in the coming years. But for now, that's kind of all we know about this particular event. You can learn more about this either from the study in the description below or from the LIGO article that I'm also posting there as well. Both of them do a pretty good job thoroughly describing the exact observation, but obviously no actual answers just yet. Now honestly, I was pretty excited to find out something new about the mysterious FRBs that we've been seeing for pretty much the past 13 to 14 years. It's still kind of a mystery to us, we still have no idea what they are. And even though we've been seeing them pretty much everywhere around the night skies, we can't really explain them just yet. If this is your first time hearing about so-called FRBs or fast radio bursts, they are literally what they sound like. They're very fast, and they're sort of like a burst of radio energy that can only be seen in certain frequencies. And for the most part, they're really fast. They only last for like a few milliseconds, so it would be almost impossible to catch them with a typical handheld radio. You would have to use a very specialized radio telescope in order to record the actual bursts happening in real time. Which is why it took us so long to actually detect them for the first time ever. The technology wasn't there yet. Now, we don't really know what causes them, and for most of them, we don't even know where they came from. But in most cases, really far away. We're talking about distances of billions of light years. And also, they all seem to be somewhat different. Some of them are really short, some of them are a little bit longer, some of them are louder than others, and some of them are repeatable and have been seen more than once from the same location. Although up to now, none of them had any patterns. And when it comes to trying to explain what's causing them, well, there are a few ideas. One of them is, of course, some sort of interaction with a pulsar or a neutron star that's causing some sort of a very unusual effect that we're seeing from a distance. Some scientists have even suggested that maybe it's related to some sort of a collision between two stars, and instead of a supernova, it produces a fast radio burst and could potentially explain what we're seeing, simply because it has to be a really powerful event for us to see these radio bursts from such a faraway distance. On the other hand, some of the theories propose that all of these effects were coming from the very powerful and very mysterious magnetars, which I've discussed in many previous videos. These are also neutron stars, but slightly different from a typical pulsar. At the same time, some scientists suggested that maybe it's an effect of a very fast spinning star. But all of this so far is not really satisfactory, and obviously the idea of aliens communicating with each other came up once or twice as well. But so far, none of these ideas really explain everything we're observing. First of all, some of these FRBs are not repetitive, meaning that a spinning star would not really explain it really well. They also seem to have slightly different features and are coming from very different galaxies, while at the same time not really possessing any features of, for example, a typical neutron star. But this new paper that just came out only a few days ago from when I'm making this video might finally help us resolve what's really happening here. Because for the first time ever, the Canadian scientists discovered that one of these FRBs has a very predictable pattern and seems to actually reoccur every 16 or so days. In other words, it has a very well-defined phase of roughly around 16 days per cycle. And this is something we've never seen before. They actually observed this unusual fast radio burst over 400 times over a period of several years, and in that period they discovered that the 16-day cycle was more or less easily predictable. Now, of all of the previous FRBs we've found, only some of them, I believe 10 or so, were actually repeatable. The rest only happened once. But of all of the ones discovered, only this one right here seems to be the one with the actual predictable pattern. All of the other ones happened once or twice or maybe several times, but there was no pattern whatsoever. And because of this discovery, we're now a little bit closer to maybe finally solving the mystery of what's really causing these unusual flashes. But once again, not really aliens at all. As a matter of fact, even if you look at these predictable patterns, it's still quite obvious that these are natural signals. They're not really all exactly the same. They always have a slightly different appearance. And so these signals can only be produced by very likely a repetitive but natural source. In other words, these have no sign of artificial intelligence or some sort of artificial communication. And interestingly, these signals seem to arrive pretty much every single hour for about 4 days straight and then disappear for about 16 days. And then come back again for another 4 days, which is really strange. It's really difficult to explain right now what could cause such an unusual pattern. And one of the possible explanations here is, or are, two celestial bodies, with an orbit of roughly around 16 days around one another. And during those 4 days where we see the signals, something probably happens and somehow manages to produce these really powerful radio signals that are visible from Earth. And then during the next 16 days, we don't get to see them because the bodies are not aligned toward our planet. So we're not entirely sure exactly what's happening here, but that's because we just don't have a theory yet, which actually reminds me of how we discovered neutron stars, or technically pulsars, and how back then people were also kind of not sure what they were, and most importantly there was a lot of talk about extraterrestrials. The idea of a pulsar or a neutron star that sends out energy and can be seen from really far away was actually very theoretical. Even back in the 30s, the scientists already believed that neutron stars could potentially exist. By the 60s, they already had actual theories formed on how we could potentially see neutron stars and how they could produce these unusual jets that you see right here on the screen. So all of this was already predicted theoretically, we just had to see them, but we didn't have the technology. The telescopes were just not as advanced yet. until 1967, when the brilliant Jocelyn Bell Burner was able to finally detect the first ever pulsar. Here's the original observation from 1967, and essentially within only a few weeks they were able to connect the observation to the available theories, once and for all confirming that the neutron stars and pulsars do exist, and this is exactly what they're observing. But prior to this, for I guess a few days at least, they actually refer to this as LGM, or Little Green Man, because when they just discovered it, they didn't really know what they were looking at, and it looked like a communication from an alien species. Which is kind of where we find ourselves right now with the FRBs as well. But the only problem here, or the main difference here, is that we don't have the theories to explain any of this. So in other words, we've almost reached something opposite of what it was like in the 60s. Our technology is really advanced, we can see things that were totally invisible to us before, something we could never even imagine, but the theories fell behind, and it's very difficult for us to establish what's causing this. And I think one of the major differences or major difficulties for modern astrophysicists is that, well, there are so many papers coming out every single day that it's become almost impossible for anyone to actually catch up with everything that's being released. So trying to identify the exact explanation here would be quite a challenge. Now, luckily for us, this particular burst came from the closest galaxy to us, and also a galaxy that's surprisingly similar to the Milky Way. Here's actually what this image looks like in real life, and as you can see, it's somewhat similar in shape to Milky Way galaxy, and because of its proximity, we could even find a way to study it in a little bit more detail. The distance here is approximately 500 million light years away from us, which is way closer than anything else, even though it does sound pretty far away. Nevertheless, this is right now our best chance to try to once and for all solve the mystery of FRBs by looking at them with everything we have and trying to discover what exactly is happening out there. Now, the way that the Canadian scientists were able to discover and also analyze this particular FRB is by using the amazing Canadian CHIME telescope, which honestly doesn't even look like a telescope at all, but it is a very powerful radio telescope that only became operational a few years ago and actually is eventually expected to discover up to several of FRBs per day. It's super sensitive and is able to detect things we could never detect before. And thanks to CHIME, and I think that stands for Canadian Hydrogen Intensity Mapping Experiment? I might have gotten this wrong. But anyway, thanks to CHIME, we'll hopefully within the next few years be able to finally resolve the mystery of these FRBs. Now, as I mentioned before, the chance of this being some sort of alien technology or some sort of extraterrestrial activity is practically null. There's almost no way that this is something artificial. But the chance of this being some sort of a natural, never before seen phenomenon that could in some way help us discover something we've never known before about, I don't know, neutron stars, black holes, maybe things like quark stars, is very high. This is probably something we just can't really imagine right now, and we need a theory to try to explain what we're looking at. And just like with black holes, neutron stars, pulsars and so on, whoever is able to explain it will very likely end up with a Nobel Prize. But until we get a better idea of what exactly this is, what's causing it, where it came from, why do some of these repeat and some don't, and are they all kind of similar in some way, I guess that's about it. But before I finish, I also wanted to thank this wonderful person whose name I think I can't really pronounce, but I think this person is from Turkey, and he initially sent me the article about this. And even though I did see the paper originally, it didn't really seem important until I read the article. And so thanks to him, I was able to cover this pretty quickly. We're going to discuss this new study that came out very recently that may actually present at least one answer of what existed before our own universe, before the universe expanded, and obviously before the Big Bang itself. But before we start though, I really have to say that right now, as of today, we kind of have no idea if anything did exist before the Big Bang, and if anything was out there before the universe came to be. As of today, as of 2020, our understanding of the timeline of the universe kind of stops somewhere right here. Basically, a few fractions of a second after the initial creation of the universe. Now, even at this point, there are still some speculations that things may have gone differently, but for the most part, we kind of don't really know if anything at all existed here. However, at least one scientist, this wonderful person, Roger Penrose, has been arguing about the idea that the universe itself has been created and destroyed several times over the eons of existence. This concept usually goes by this name, although sometimes it's known by different names as well, and generally we refer to it as cycles of time. And even though you may have never heard of Penrose before, he's actually on par with Stephen Hawking in terms of various ideas and theories he proposed over the years. He's one of the most distinguished modern theoretical physicists and has won a lot of different awards. But anyway, that's not really the important part. Today we're really trying to figure out what exactly is he proposing and does it have any merit. So in his theories, what he suggests is that if we were to try to go back in time and essentially reach the point where the Big Bang started happening, which is of course this point right here somewhere, there might be signs for us, or there might be actual evidence there that suggests that something else may have existed. And for many years he suggested that we can actually see these signs in the so-called cosmic microwave background. Now you might remember what cosmic microwave background is. This is the so-called CMB. And essentially this is the first light we get to see from the beginning of the universe, when approximately 375,000 years ago, the universe itself cooled down enough for various protons and electrons to start combining, creating a lot of neutral atoms and thus allowing the light to actually move around the universe. It was no longer opaque, it was no longer absorbing light. So some of this first light is what we see in the CMB. And over the past few decades, our ability to see the CMB has improved quite dramatically. This is from back in 2003, and this is the most recent one from 2013. So the accuracy of us seeing this light, this first light in the universe, is improved enough for us to actually see specific details in it. And according to Penrose, in this CMB, in these lights, you can actually find clues suggesting what happened before the Big Bang. And for a very long time he was absolutely adamant, he was pretty certain that we could actually see the remains of the past universe in this CMB. In other words, we could possibly see the signs of the previous universe or whatever else existed before our own universe. And so it's really interesting that he's been pursuing this for many years now, and a few weeks ago his team released another paper suggesting that there's actually quite a definitive sign in the CMB that suggests something may have happened before our universe. And that something was very likely extremely massive, extremely large black holes that disappeared over time. So here's what they actually proposed they found in these observations from the cosmic microwave background. By looking at the older data and combining it with the newer data, they were able to identify several pieces of evidence suggesting that there were these unusual and relatively large rings that were apparent in some of the data that could only be explained as some kind of artifact from whatever happened prior to the existence of our own universe. And some of these rings and some of these unusual formations in the CMB are usually explained with the early turbulence in the existence of the universe, but some of them are difficult to explain without introducing some other ideas. And in this case, they believe that some of these very specific formations can only be explained by something else that happened in the past. Basically something that influenced our own universe even before the universe began itself. And they're proposing the following. They're basically saying that these extremely massive black holes that existed at the end of the last universe started to emit a lot of Hawking radiation, which we know very likely is being emitted by all kinds of black holes in our own universe right now as well. And due to the sheer size and mass of these black holes, the effects were so large that they now are visible in our own universe through these unusual rings and other deformations in the CMB. Which kind of implies that the last universe very likely ended with the existence of these really massive black holes during the so-called last black hole age of the universe. Today we believe that maybe at the end of our universe we'll have something similar where nothing but black holes are left, and eventually even these giants will evaporate, leaving nothing behind. So in some sense, the evidence from the CMB does seem to suggest, at least according to Penrose, that this is exactly what happened with the last universe before the Big Bang caused our universe to begin as well. So in other words, what he's suggesting is that all of these ancient black holes from the previous universe, as they evaporated one by one, left little marks that are now seen in the CMB of our own universe. And this is something that's kind of really difficult to wrap your head around, but he does explain it using a lot of theoretical physics and a lot of modern theories that do kind of suggest that maybe he's right. However, there is a small problem with all of this, and the problem is that according to his theories, all of the universes will then end the same. They will all end up with the so-called Big Crunch, where essentially the entire universe slowly condenses into a tiny point yet again until the restart of the new cycle. But the problem here, of course, is with the evidence we have from the last year or so. There was a study that seems to actually discredit this, suggesting that the universe will most likely end up ripping itself apart, the event we refer to as the Big Rip. The evidence for this was quite substantial, and I've talked about this last year, so in that sense there's a bit of a contradiction. Unless, of course, our universe is completely different from the previous universe. Maybe what's happening now is something unique and something that hasn't happened before. But at the moment, there is nothing to say that he's actually wrong, and there is a lot of evidence to suggest that he is right. Unless someone can explain some of these observations in the CMB using some other idea or some other theory. For now, there's no better explanation. And although still theoretical, this proposal can of course explain a lot of other things. There's actually a lot of really interesting other theories that he proposes, including the so-called information panspermia, which basically implies that technically by using the communication between the previous universe and this universe, some super advanced extraterrestrial intelligence could have actually found a way to transfer all of the information about life to our universe to begin it here as well. And all of this cosmological information could have actually been also stored in the CMB, eventually making its way to various planets across the universe. Now this is a really far-fetched idea, there's really currently no proof of any of this, but it's still an interesting idea to explore, especially as we learn more and more about the CMB itself. There are still quite a lot of mysteries about this unusual background radiation. But unfortunately, all of this is still very theoretical. It's going to be extremely difficult to prove any of this, and we'll need a lot more, much more powerful observations of both the CMB and the universe around us to try to see if any of this makes any sense. At the same time, trying to disprove this is also quite difficult because, once again, we don't have enough data or any alternative theories to try to suggest that these ideas are incorrect. So for now, it's something to think about, something to ponder, and I guess in some sense, it's good to know that at least one scientific study was able to prove the existence of so-called cyclical universes across the ages. In other words, the universe being created and destroyed. We obviously don't know how many times, or if the other universe was different in any way in terms of the actual physics. But all we know for now is that there are definitely going to be a lot of follow-up studies to try to talk a little bit more about this, especially from the theoretical physics perspective. But until then, unfortunately, that's kind of all we know. It's definitely a really cool idea, but for now, it's kind of just an idea. Now, one of the reasons I wanted to start with the supernova explosion is because, well, first of all, this is probably the most commonly known explosion in space. These are events that do happen quite frequently, and we've seen at least a few of them even in our own galaxy in the last few hundreds of years. But more specifically, for the most part, they do tend to have a relatively similar energetic output. In other words, they produce a relatively similar amount of energy. It's a huge amount of energy though. And one of the ways of imagining how much energy it actually is by imagining our sun and then thinking of how much energy it will produce over its entire lifetime. So here, if we wait roughly around 10 billion years, and I'm going to do this manually by advancing the time, at some point our sun is going to start changing in size and growing larger and larger and larger, eventually enveloping pretty much most of the terrestrial planets in our solar system, including very likely Earth. Following this, it will lose its outer shell and become what's known as a white dwarf. But right before this happens, it will have lived approximately 10 billion years or so. And in those 10 billion years, it will have released the amount of energy not so far off from the unit we call Pho. And Pho is a unit that some of these scientists had to come up with in order for them to easily study supernova, because it was just such a huge amount of energy that it would be difficult to always express units in terms of really big numbers. So 1 Pho is roughly equivalent to the total amount of energy produced by our sun, and is also not very far off from the energy produced by a typical supernova. But supernovae are far from being the most powerful explosions, not even close. Some of the most ridiculously powerful outbursts often happen around black holes, and in most cases around these central supermassive black holes in the middle of most galaxies, and these explosions can be ridiculously powerful. Now, even in our own galaxy, the Milky Way, we've already seen several signs of such previous explosions or outbursts in the past few millions of years. The so-called Fermi bubbles that you see on the screen right here are one such sign of an event that was very likely about 10,000 Pho in power. So basically about 10,000 times the typical amount of energy produced by a supernova. So when it comes to the outbursts and most massive and most powerful explosions, basically it's all about supermassive black holes. But it just so happens that very recently, scientists, by looking around the night skies, have identified a very unusual galactic outburst that happened roughly around 7 billion years ago in a galaxy that's about 15 billion light years away from us. Now, because I always get a few people in the comments below asking about how is it possible that something that's only about 7 billion years old is about 15 billion light years away from us, which would technically make it older than the universe itself, I decided to quickly explain it in this video, although there is a much larger explanation in one of the previous videos. Anyway, the idea here is that because the universe is expanding, even though two galaxies might have been relatively close to each other about 7 billion years ago, they're now much farther away, and so for the light to travel from one galaxy to another, it will actually take it much longer than it would originally. And so because the galaxies are slowly moving away from one another, the light will take longer and longer to reach as the universe expands. And so by looking at this galactic cluster known as SPT 0528, the scientists were able to see these unusual formations, which upon further analysis turned out to be these unusual holes in the middle of gas inside the galactic cluster. And the only way we can explain these unusual holes is if a sudden outburst comes from two directions of a supermassive black hole, and all of this outbursting matter basically creates a kind of a hole in the middle of the gas cloud. And this cloud altogether is really big. It's actually several times bigger than the Milky Way galaxy, suggesting that these holes were created by one of the, if not the, most powerful outburst that has ever occurred anywhere in the universe, at least from all of the ones we've seen so far. By using the precise size of these cavities and trying to determine the actual energy released, they established that the energy was equivalent to about 10 billion supernova, all happening at the same time. And this is definitely the most powerful event we have seen so far, or at least the effects of which we were able to figure out by looking at the gas cloud. That's also approximately 1,000,000 times stronger than the event that happened in our own galaxy, and it's probably one of the most powerful events that has ever occurred anywhere. Now, we're not really sure what could have caused this unusual outburst or this huge explosion, and we obviously have no idea what effects this had on the parent galaxy, but we can probably imagine that most of the stars and most of the planets in that galaxy suffered quite a lot. This unusual event also produced an extremely powerful radio source in the middle of this particular galaxy, and if we were to look at this in radio frequencies instead of visual light, we would witness the brightest object in the night skies. Which is really not that surprising, because the brightest radio signal very close to our galaxy is this right here, our neighbor Centaurus A, which is the loudest radio signal in the night skies right now, mostly because it's much closer than the other galaxy. And this galaxy also possesses these two very large lobes that were created through an outburst several million years ago, and it's very likely this is how the other outburst was produced as well. Now, at this point, we're not really sure what exactly could have caused such a huge explosion. I mean, we're talking about a lot of mass suddenly falling into the black hole and creating such a tremendously powerful outburst that I don't really think we have a theoretical model that would be able to explain this very easily right now. Most of the black holes we've witnessed so far cannot really explode that much. So something else very specific might have occurred here, and this is something I'm looking forward to hearing about in the future once the scientists behind this paper figure it out. But once we learn more about what happened in this galaxy, and once we find out what exactly caused this really powerful explosion, I'll make sure to follow this up with another video. For now, it seems we've discovered the signs of the biggest ever outburst or explosion ever in the universe. And that's, I guess, not including the Big Bang, but that's not really an explosion. Here we're talking about an actual very strong outburst of energy equivalent to, well, as I mentioned, 10 billion supernova. And if a similar event occurred in the middle of our own galaxy, it's very likely it would cause the complete extinction of life on our planet within only a few months. Even if we find a way to hide somewhere, like in caves or underneath the mountain, the energy released here would actually strip the planet of atmosphere, and so we'll just eventually maybe suffocate. But anyway, let's stop here, because at this point everything else is speculation. So first of all, when we look into the really early universe, there are certain expectations that we have, mostly based on theories that we have. For example, we expect the early universe to have a much wider variety of really massive stars, and very likely a lot of stars that no longer exist, such as the so-called population 3 stars. And we also expect there to be a lot of really small galaxies, and the universe itself is actually not as transparent as it is today and will be more likely a lot more opaque. So these expectations are all based on our current understanding of the universe. But first of all, let's talk a little bit more about the types of stars that we expect there to be in the early universe. Generally speaking, today we know that there are quite a lot of different types of stars, and there's a lot of variety in different shapes, different masses, and the way that they act as well. But all of this together can be summarized based on the actual components inside the stars. So based on the chemical composition, we can define most of the stars, if not all of the stars, as 3 main types. The newer, more developed stars like our Sun are what's known as population 1 stars. The reason we call them that is because compared to other stars in the universe, they have a lot of metallicity. But when you hear astronomers talk about metallicity, all they're talking about are elements that are not hydrogen and are not helium. So literally everything else except for hydrogen and helium. All stars today pretty much mostly are made up of hydrogen and helium, but they always have other elements, and we refer to them all together as metals. And this is simply a definition, and it has nothing to do with actual metals here on Earth. And in case of our Sun, it's about 1.4% metallic, meaning that about 98.6% is hydrogen and helium. Everything else is other stuff, like oxygen, carbon, nitrogen, and obviously metals like iron and lithium. A lot of the younger stars, and also a lot of the stars we're kind of interested in when looking for exoplanets, are normally population 1 stars, because these are the stars we expect to have actual terrestrial planets. But then there are population 2 stars, which are actually much older, but also, for the most part, are predominantly made out of hydrogen and helium with very little everything else. Over the years, a few of these stars became really popular and really famous actually, mostly because of their age that we've determined through measurements of metallicity and other properties. For example, this is the famous Methuselah star, which made the news when some scientists claimed that it was even older than the universe, which is of course impossible, which in reality was most likely due to the miscalculations when it came to actual properties of the star. Nevertheless, it's definitely older than 13 billion years old, and similar to other population 2 stars, they're all extremely old, usually over 12 or more commonly 13 billion years in age. This of course means that these stars existed for most of the existence of the universe and were very likely created from the early material from early supernova. But this is where the question arises about the next population type, population 3 stars. The much older and much earlier stars that created these initial supernova. And this is what the scientists have been looking for a very long time now. We theoretically predict their existence because of what we're seeing inside population 2 stars. For example, we see the material inside population 2 stars that suggests supernova created them. But these supernova must have come from somewhere. Something must have delivered all of this material to create population 2 stars, and we've always believed that this something was the mysterious population 3 stars, which are an entirely different species of stars that we don't think can even exist anymore. One of the reasons why their existence was possible in the beginning was of course because the universe was first of all more dense, and it was also much hotter. So these stars eventually reached really huge masses. Some of them were probably thousands of masses of the Sun, something that's currently actually impossible. The most massive star we've discovered so far is the star in the R136 system known as R136A1, and this one we believe might be over 200 masses of the Sun, but even this is extremely unstable and is going to go supernova. But these stars do not represent what it was like in the early universe. They actually probably even have completely different shapes and obviously composition. The early stars had pretty much mostly hydrogen and helium with just tiny bits of lithium and beryllium and maybe some other lighter elements. We don't think they also lasted very long either. They probably only lived for a few million years before exploding in these really ultra powerful supernova that did a lot of things to transform the universe. So most of the modern theories today focus on these stars as the explanation for the so-called reionization period. This was a very interesting period where the universe transformed from being somewhat foggy and opaque to being completely transparent. And the reason we call it reionization is because whatever was ionizing the matter made it transparent. We think that this is what population 1 stars did. All of their extremely powerful emissions and also all of their extremely powerful supernova most likely resulted in the entire universe transforming into transparent as it is today. And so by using the Hubble Ultra Deep Field investigations, the scientists were trying to look into this early universe when it was basically transforming from being opaque to being transparent, and they were trying to see what was causing it. Their expectation was that they're going to find a lot of signs of the mysterious population 1 stars, probably see their emissions, probably see a lot of supernova going on, and maybe see something else to suggest that our theories are correct. And so this is exactly what the scientists behind this study did. They essentially used one of the earlier investigations and developed a new technique and looked into the early universe and also employed what's known as a gravitational lensing effect to try to see as far and as deep into the universe as they could. To do this, they used this famous galactic cluster that has a gravitational lensing effect in it, known as MAX J0416. And by using this cluster, and by trying to subtract any unnecessary light, they were able to see the absolutely earliest possible light that this galactic cluster emitted. And essentially they were looking into this part of the universe when the universe was only about 500 million years old. With the main purpose, of course, being discovering these early stars and trying to see if our theories on population 3 stars and reionization is correct. Well, it turns out that they did not find the population 3 stars. There were no signs of any of these early stars in this early universe, which of course means that the early universe itself is, once again, a lot more mysterious than we initially thought. It also implies that the so-called reionization period may have been caused by the tiny galaxies present all over the place and not necessarily specific types of stars. This is kind of what they observed in the early universe. They've discovered a lot of smaller galaxies. A lot of galaxies that were already formed and were emitting a lot of light. Which is really surprising because we didn't think galaxies developed so quickly. All of this means that galactic formation happens much quicker than we thought originally. And it also means that early young galaxies played a much bigger role in reionizing the universe than the stars themselves. The mysterious population 3 stars may actually have been in existence much earlier, or something else is going on here and these early stars may have never existed to begin with. And if all of these early galaxies that already formed by about 500 million years of the existence of the universe were responsible for the reionization, we kind of have to now understand how they did that, how they were able to reionize the entire universe with much weaker but also, I guess, more populous population 2 stars. And we also have to figure out where and when these population 3 stars existed, if at all. Now today we believe that if population 3 stars existed, there is actually a chance that at least one of them might still exist in our galaxy as well. The scientists calculated that if during the early universe some of these very early supernova created a chunk of matter that eventually turned into a star that's about 80% the mass of our sun, it would still exist even today and would not have actually disappeared just yet. And we should be able to find these unusual stars somewhere out there, assuming of course population 3 stars even existed. All of these stars without exception would have extremely low metallicity, unexplainably low as a matter of fact, but other than that it will be very difficult to tell if it's actually a population 3 star or a population 2 star. And since these early stars would very likely have no planets whatsoever, they would also be completely by themselves. So there might still be a chance of discovering one of these unusual ancient stars somewhere in our own galaxy. But this obviously does not resolve the mystery of the complete absence of these stars in the early universe so far, and it also doesn't explain how early galaxies could form so quickly in this early universe. So there are still a lot of questions to answer. Unfortunately, as of today, there are no new plans to create even more accurate images of this so-called ultra deep field, so the scientists have to use older data to try to discover something else out there. But considering most of these discoveries were only made in the last 10 years or so, I can only imagine that our advances are going to be even more dramatic in the next 10 years. So I'm only more excited to see what the scientists will discover in even earlier universe once we're able to create even more accurate images or analysis of older data. But until we discover more, that's pretty much it. You can also check out one of the older videos I made about the so-called deep field that Hubble released a few years ago, and it's actually a really mind-blowing image. It has thousands and thousands of galaxies in a single picture, and some of them look absolutely magnificent. The farthest galaxy ever discovered. The galaxy that's going to appear in your view any second now. This galaxy is extremely far away. This is literally as far as we can actually see physically, at least for now, because we don't have a better telescope. And this is the galaxy we're talking about today, known as GN-Z11, where GN refers to its location in what's known as the Good's North Field of Galaxy. And this is actually what all of it looks like, and this is the image taken by Hubble a few years back, where Z11 stands for the redshift of this galaxy. And recent studies have tried to estimate how far away it actually is by trying to recalculate the value for this redshift, but also tried to discover anything else unusual about this galaxy. And they have discovered something strange about it. But before we talk about this, why is it weird to begin with? And also, what does the Z11 redshift mean? Well, as you probably know, when it comes to cosmological distances, we don't necessarily measure things in kilometers or even in light years. At really far away distances, this becomes almost impossible, but we can measure distances in what's known as redshift. The natural shifting of all of the light as it travels across the universe, becoming slightly less energetic with time. We think it's because of the mysterious dark energy, but at this point we are not really going to talk about this because we don't really know why. We just know that it's something that happens naturally. So in this case, if we were to actually take a look at a really far away galaxy, or in this case many different galaxies, some of them would actually appear more red than others. And this becomes even more pronounced as we start looking deeper and deeper into the universe. Here, for example, you can see how redshifted this particular galaxy is. Now, naturally, by using this redshift and also by using the calculations of Hubble constant, we can then start establishing various distances across space. Or we can also just use a calculator like this one right here, created by Ned Wright from UCLA. And the formula for redshift is pretty simple. If you know what the light is supposed to be in terms of wavelength, and you then compare it to the observed wavelength, you can determine the value of z. So let's just say you looked at a galaxy and you determine that the value is z equals 1. At z equals 1, the distance to this particular galaxy is roughly around 11 billion light years away from us. Okay, well that's awesome, but how about this galaxy? The redshift here is 11. How far away would this be from us currently? And the value you get is about 32.1 billion light years. That's right, it's about 32 billion light years away from us. Now obviously some of you might be asking, but the universe is only 13 billion years old. Don't forget, the universe has been expanding, so because of the expansion of the universe, the galaxy was also moving away from us as the universe was expanding, and so this distance is much larger now. But here we also see that the light traveled for 13.3 billion years, meaning that this galaxy is about 400 million years old, at least in this particular picture. And this is very interesting because this is the time when we believe the universe itself was still opaque. It wasn't actually that transparent just yet. In other words, it was after what's known as the cosmic dark ages, when the universe was filled with this neutral hydrogen gas that wasn't actually letting through any of the light. It was literally just foggy everywhere in the universe. And it was really because of these first stars that formed in the first few hundreds of millions of years of the existence of the universe that we actually started to experience this period known as the reionization. This is essentially when the universe finally became transparent and started to let through all of the light. We're not entirely sure if it was really the stars or the galaxies or a combination of both that kind of caused all of this, but we know that before this it was really difficult to see anything. And it just so happens that, as you can see from this particular image, the galaxy that we've discovered, this galaxy known as GN-Z11, appeared right at the start of the reionization period. It's essentially possibly the only galaxy we'll ever see because everything else was still invisible, it was still opaque. In other words, the universe itself was not actually letting through any of the light, but it let through this particular light from this particular galaxy. And since the original discovery, we were able to learn quite a lot of really cool things about it. Now, first of all, this is what we think it may have looked like back then. It was essentially an extremely bright, very sort of a starbursty galaxy with a lot of formation of various stars, but it was also much smaller than the Milky Way, about 25 times smaller. It also contained maybe about 1% of the total mass of the Milky Way, but was obviously forming stars much faster, maybe about 20 times as fast as the Milky Way right now. But also don't forget that this galaxy is extremely young. It's only about 40 million years old here, and that means that these stars are basically just brand new stars that just appeared and started to form the galaxy as we see it. And a lot of the light that they're emitting here is actually ultraviolet light, which is what we expect from these very powerful, very new stars. This is also what we see from some of the other galaxies near us. But because of the tremendous redshift of 11 essentially, all of this ultraviolet light becomes this very, very dark red light. It's essentially shifted by a tremendous amount, essentially making all of the other light, like such as visual light, invisible to us unless we look at this with some sort of an infrared telescope. But one of the recent studies that you can find in the description below examined this galaxy in more detail, discovering certain really unusual features that we really didn't expect. Here they were looking at these ultraviolet emissions from very specific chemicals, trying to identify known chemicals to us and thus calculate the exact distance to this galaxy once again, making the exact value this, 10.957. Which makes this about 420 million years old and makes it just a little bit closer than we initially thought, but still really far away. Still the farthest galaxy out there. But at the same time, the same team using the same data also reported something we clearly did not expect at all. They discovered what's known as a gamma ray burst, an extremely rare event that we think only happens in a single galaxy maybe once every million years or so. And their observation does suggest that the galaxy here became extremely bright for at least 20 seconds, which they refer to as the flash, but it could have been the typical gamma ray burst that we usually detect in various galaxies. Once again though, this would be an extremely rare event, and the fact that they discovered something like this is really absolutely mind-blowing, because it's almost impossible to detect a gamma ray burst in a single galaxy by just looking at it for a few minutes. And this is what happened here. Now obviously there are going to be possibly other explanations, such as maybe this was a satellite signal, or maybe this was a terrestrial gamma ray flash, which do occur coming from planet Earth as well, so maybe this is what was actually seen completely by accident. But in reality we're not going to know until further investigations and until further observations, longer observations of this unusual and strange galaxy. However, if this is a gamma ray burst or gamma ray flash, as has been suggested by the follow-up papers that came out a few days ago, this can only suggest one thing, that these gamma ray flashes or gamma ray bursts were probably a lot more frequent and a lot more common in the early universe. It just means that the universe back then was extremely active and a lot of crazy things were going on everywhere. And this kind of makes sense. I mean, black holes may have been producing a lot more of these gamma ray bursts, and also naturally a lot of different powerful supernovae could produce them as well, but it means that we might be underestimating the number. These could be extremely common to the point of being almost a daily occurrence, which is something that a lot of scientists currently cannot explain, or something that we can't even start to explain. But nevertheless, this is an exciting galaxy and it's definitely worth studying it a lot more. And what's really cool about it, something that I forgot to mention, is that it's also located in a very well-known constellation known as the Big Dipper, also known as Ursa Major. It's going to be extremely difficult for you to locate this object because it's basically in the middle of dark space, but next time you look at the Big Dipper, which is basically right here, and with the Ursa Major being the rest of the constellation, the galaxy itself is right in this location. So that's something for you to know next time you look at the night skies. Anyway, on that note, that's kind of all we've learned about this amazing galaxy, but it's also something that we really didn't expect. And if you've enjoyed this video, please subscribe, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something you may have not known before. Also, support this channel on Patreon or by buying the Wonderful Person t-shirt you can find in the description below. I'll see you tomorrow, peace out, and as always, bye bye.